Hey everyone. So today we're going to be looking at types of chemical reactions and how we can predict the products of certain chemical reactions. So if you can, follow along with your graphic organizer and let me know via email if you have any questions. So let's go ahead and get started. As far as this goes, there are really 4/5 different types of chemical reactions. Now, these are very generic titles, and you can go ahead and split up each one of these into different types of chemical reactions as well. But just for the general chemistry class, we should know that the 5 types of generic reactions are synthesis reactions. And think about the word synthesis, right? Coming together. Decomposition, breaking apart. Single and double replacement, those two are very similar types of chemical reactions. And then the last type is going to be a combustion reaction. So first things first, when we go ahead and try to predict the products, we should know first the type of chemical reaction. I'll go through each one of these specifically as we are predicting products. As we're trying to predict the products, when you have a product by itself that is an element, remember elements are made of one type of atom, it's really only going to be either the element by itself or a diatomic element. Now, sodium is going to be a good example of an element by itself is just Na. But as we know, oxygen is one of the 7 diatomic gases. So we're always going to list it as O2. Don't forget, Brinkelhoff is our mnemonic for diatomic gases. As far as predicting products goes, whenever we're trying to make compounds, we should always consider the ionic charge. We spent a lot of time on this talking about the charges from the elements on the periodic table, so hopefully you guys have that down at this point. For example, magnesium chloride is going to be composed of magnesium and chlorine ions. Magnesium has a +2 charge, chlorine has a -1 charge. You're going to get the formula MgCl2. Silver nitrate, silver has a +1 charge. Nitrate is one of the 8 polyatomic ions I expect you to know, has the formula NO3. So it's going to have the formula AgNO3, +1 and the -1 end up canceling out. So let's go ahead and look at some of these common examples of synthesis reactions and really show you kind of what's going on with this. So a synthesis reaction is going to be when multiple atoms combine to form one product. So the idea is one product will be a signifier that this is a synthesis reaction. So magnesium and oxygen. So usually first thing that students want to do is really just kind of combine these two things to just say MgO2. And I want to first off start by saying that is not how you approach these. You don't look at the amounts beforehand. The amounts beforehand are important for balancing these chemical reactions, but as far as actually figuring out this chemical, we want to go ahead and consider the charges, right? So we're always making a compound. The only thing that 2 elements can do is combine to form a compound. And remember, all compounds in this whole prediction of products unit are going to be ionic compounds. So the charge of magnesium from the periodic table is +2. The charge of oxygen from the periodic table is -2. So we know that these two will come together in a 1-to-1 ratio. The compound is going to be MgO. Now, as far as this goes, we have something that is not balanced, a chemical reaction that is not balanced. So we need to go ahead and now balance it. So that's where this 2 comes into play. So there are 2 oxygens on the left, 1 on the right. Put a 2 in front there. Now I have 2 magnesiums on the right and 1 on the left. So we put a 2 there. The charges are just to help us figure out what the products are. Now, remember, magnesium and oxygen gas by themselves are not charged. We're just using what the normal ionic charge is going to be. Let's go ahead and try this again. Rubidium. Rubidium has normally a +1 charge. We know that from the periodic table. Sulfur has normally a 2- charge. So +1, 2-. The compound that is going to be formed will be Rb2s. So 2 rubidium ions for every 1 sulfide ion. Now, elemental sulfur is S8. It forms this like molecular ring. It's kind of a cool substance, a cool molecule here. So quite literally what's happening is all 8 of these atoms are breaking apart, and each one of those 8 sulfurs is going to combine with 2 rubidium atoms. In order to do that, we are going to make a total of 8 compounds on the right-hand side. And notice the coefficient here is going to be 16 for rubidium. So it's quite a large coefficient. Last but not least, go ahead and try this one. Pause the video, try it on your own, see if you can get it. I'm gonna go ahead and start this one now. So lithium normally has a +1 charge. Fluorine normally has a 1 minus charge. So this is a 1-to-1 ratio, LiF. The fluorine has a subscript of 2. The lithium now will be a 2 coefficient there. So generally speaking, when we're looking at synthesis reactions will combine the elements based off of their charge and make one compound. You know it's a synthesis reaction when all you're doing is combining elements. On the flip side, we could have decomposition reactions. Decomposition reactions are kind of nice. These are going to be basically when we have one reactant and then the arrow. As far as this goes, when that reactant is a compound with 2 elements, it will really just break up into those elements. So, for example, H2O will decompose into hydrogen and oxygen. And whenever we write an element by itself, we have to ask, is it a diatomic? Well, hydrogen, Brinkelhoff, yep, is. Oxygen, O2, yep, that is Brinkelhoff, right? So these are the products of this chemical reaction where you just have a compound and then an arrow. The next thing we need to go ahead and do is balance the reaction by putting a 2 in front here and then a 2 there. Magnesium chloride is another good example of a compound that contains only 2 elements. So when it decomposes, it's really just going to break down into its constituent elements, magnesium and chlorine. Is magnesium a diatomic element, Brinkelhoff? No, so we don't put the subscript 2. Chlorine is a diatomic, so we're going to put the subscript 2 there. This one just so happens to break up into its same ratio. So this one's already a balanced chemical reaction by predicting the correct products. The last example that I want to look at here is potassium chlorate. Potassium chlorate, notice, has 3 3 different atoms in it, potassium, chlorine, and oxygen. And for these ones, I don't want you to worry about the specifics of them. Just know that they don't break up into their individual elements. These are a little bit more special. For this, it's going to break up into potassium chloride and oxygen gas, potassium chloride and oxygen gas. For as far as balancing it goes, we have a 3 and a 2. So we're just going to kind of flip those coefficients up. And then we need a 2 there. When you're looking at a decomposition reaction, know that the reactants are breaking down into multiple products. Generally, they're going to be elements. They don't always have to be, but for the compounds that contain only 2 elements in them, then they're going to break down into the indistinct elements. For the last 2, or rather next 2 type of reactions, we need to look at some generic rules for how we combine and switch partners. So these are going to be the single and double replacement reactions. For single and double replacement reactions, we should know that cations will replace cations and anions will replace anions. Positively charged things flip with positively charged things. Negatively charged things flip with negatively charged things. It might also help to think of it as metals replacing metals and nonmetals replacing nonmetals. This doesn't always work, seeing as not all cations are metallic and not all anions are nonmetals. But at the same time, most of them are, as I'm sure we know. Next, I do want you to kind of keep on the back of your mind when we're doing these, think about the charges of the ions. Oppositely charged things want to bond with each other, like charged things don't. So let's go ahead and look at a single replacement reaction. This is going to be when an element replaces another element that is currently in a compound. So you can kind of look at this diagram down below. The element A is replacing element B to form B by itself and the new compound AC. So we know that this is a single replacement reaction because we're looking at a single element and a compound. You always have a single replacement reaction when you have an element and a compound. So as far as this goes, as far as this chemical reaction goes, we know that the charge of silver is 1 plus. We know that the charge of nitrate, which is a polyatomic ion, right, is 1 minus, either from your chart or having it memorized. And copper generally forms the charge 2 plus. Sometimes it forms 2 minus. We'll jump into predicting the charges of transition metals later. So based off of this, copper, do you think that wants to bond with silver or with nitrate? Well, if copper is generally something that is positively charged, it's going to want to bond with something that is negatively charged. So you're going to go ahead and get copper nitrate, and the ratio that those two ions come together is 2 to 1, right? The charge of 1 minus, charge of 2 plus. Silver was kicked out and is now all by itself. Generally, when we write an element by itself, you have to think, is it a diatomic? Silver is not, so we're good to go there. Rubidium chloride reacting with fluorine gas is next. The same kind of thing. We're going to look at each respective charge. Rubidium has a charge of 1 plus. Chlorine has a charge of 1 minus. When fluorine has a charge, it's going to be 1 minus. So we're going to go ahead and look at, what does fluorine want to bond with, rubidium or chlorine? Well, if fluorine has a -1 charge, it's going to want to combine with the positively charged thing. And we'll go ahead and get rubidium fluoride, RBF. And notice it's a 1-to-1 ratio because of the charges. The 2 has nothing to do with figuring out what the products are going to be. This ends up kicking out chlorine, and chlorine's all by itself. Whenever we have an element by itself, we ask ourselves, is it a diatomic? This will be Cl2. And the reason that is because chlorine is a diatomic. And for these two reactions, we now need to go ahead and balance them out. Let me go ahead and erase some things here to make it a little bit clearer. So we're going to go ahead and balance these two chemical reactions out. Notice that the first chemical reaction has 1 copper, 1 silver, 1 silver. Oh, and then 2 nitrates. I like to think of the polyatomic ions as groups, and 1 nitrate. So we're going to put a 2 in front here, and that also doubles the amount of silver. Same thing kind of happens down here. We have 1 rubidium, 1 chlorine, 2 chlorine. So we're going to put a 2 in front here, and that changes the amount of rubidium, so that requires a 2 there. And then everything is balanced for that second chemical reaction. Moving on to the next type of chemical reaction, we have a double replacement reaction. Now, as far as a double replacement reaction goes, they look very similar to single replacement reactions. What's essentially happening here is that an ionic pair is switching with another ionic pair. So silver nitrate is going to combine with sodium chloride. When this happens, the components, the anions, will switch partners with the cations. So if we kind of remind ourselves what the charges of each one of these are, silver, right, is going to have a 1 plus charge. Nitrate, that polyatomic ion, has a 1 minus charge. Sodium has a 1 plus charge, and chlorine has a 1 minus charge. Based off of these, we know that silver with the positive charge is going to want to bond with the chlorine with the negative charge, and it's going to form a 1-to-1 ratio based off of those charges. Same thing with the sodium and the nitrate. Sodium and nitrate will form a 1-to-1 ratio because each one has the same charge, same but opposite charge. Last but not least, if we look at hydrobromic acid or hydrogen bromide, generally hydrogen is going to have a 1 plus charge. Bromine is going to generally have a 1 minus charge, or 1 minus charge. Let's go ahead and erase that there, 1 minus. Calcium has a 2 plus charge. Hydroxide, the polyatomic ion, has a 1 minus charge. And as we can kind of see here, bromine and calcium will form a bond because they are oppositely charged things. So we're going to have CaBr2. We know it's a 2-to-1 ratio because bromine has a 1 minus charge and calcium has a 2 plus charge. And that leaves us with OH minus and H plus. Now this one's kind of fun. It's really easy to write HOH because, right, positive hydrogen and a negative OH. But what is HOH? HOH, if you haven't figured that out, is good old-fashioned H2O. It's water. So whenever you have hydrogen ions reacting with hydroxide ions, this will always form water, liquid water. Now, the last type of reaction that I want to go ahead and discuss is going to be a combustion reaction. These are the only molecular reactions that we're going to be talking about. Remember, molecules or molecular refer to covalent substances. Now, as far as combustion reactions go, these are always going to be organic molecules. And remember, organic molecules contain carbon reacting in a highly exothermic way. Exothermic means that it's releasing energy when it reacts with oxygen gas. The hydrocarbon or organic molecule will always react to produce carbon dioxide and water. Now, this looks like a single replacement reaction. This looks like oxygen, an element, is reacting with a compound. The main difference, though, is that this compound is not ionic. It is a molecule. Combustion reactions always occur with a hydrocarbon or organic substance. The products of this chemical reaction will always be CO2 and H2O. It's kind of nice. We don't have to consider um, ionic charge with these because once again, this is not ionic. The hard part about these is generally balancing. I always like to say for combustion reactions, balance oxygen last. We have two carbons, therefore we put two in front of the carbon dioxide. We have four hydrogens, so we're going to put a two here. Two times two gives us four hydrogens in the water molecule. And then we have a total of 2 times 2, so that's 4 oxygens here, 2 times 1, that's 2 here, so for a total of 6 on the left side. So we're gonna go ahead and put a 3 over here, because 3 times 2 is going to be 6. And this is our last chemical reaction here. So thanks so much, guys. We'll talk more about this in class tomorrow. Have a great day.